Welcome, everybody. It's July 27th, and this is the second in a set of 6 classes on the history of understanding science from the inside via the method of LaRouche. We've got a hybrid format for this. There's people here in the room. There's people on Zoom. On Zoom, if you'd like to speak up, raise a question, please raise your hand so we know, and you're definitely encouraged to. There was a reading packet that you'll find in the on the course website, on the video description later, and we're going to be reading some excerpts from this. So if you have it on hand, you can join in on reading those when we come to them. So briefly to situate what we're doing this week in terms of what happened last week. So on Sunday, we read Plato, and we got a sense from his allegory of the cave, from his metaphor of the divided line, about the relationship between our senses and knowledge. Plato likened our senses to seeing irregularly cast shadows on a crooked cave wall rather than seeing reality itself. And he said that to reach the highest truths, you really don't get there from your senses. You use them to create ideas that then lead you to ideas that have their own reason to exist, not determined by the senses. And we're going to find out today an example of doing that with the case of Johannes Kepler, who left Plato's cave, hypothesized a cause, an idea, and then used that to understand astronomy, unlike everyone who came before him, who was focused on looking at the wall of the cave, the planets moving along the wall of the cave being the starry background. And he said that he wanted to know why they were moving, not describe the shadows. So this was applying what Plato had laid out. It was applying what we had from Cusa, applying this to create a new science and to answer a question that other people didn't even ask before. Let me just remind one thing from last time. We ended with a quote from Nicholas of Cusa, who pointed out that real equality, true equality, pure equality could exist only in God. God is equal to God, but there's nothing else that is so equal it couldn't be more equal. And from that, Cusa said, well, that means that there are no created circles. You might imagine a circle, and if you're thinking about geometry, there's a circle in your mind that you're working with. But if you actually make anything, it's not a circle. There's no circle you could draw or circular motion that would be so ideally circular that it couldn't have been yet better. In a circle, every point's the same distance from the center. Pure equality. He says that can't happen. He says that the Earth must move, that the planets cannot move in circles. So this is already kind of floating out there, leading into Kepler, and we'll find out how Kepler put that into practice. So with that, I'm actually going to show a video. Oh no, I'm sorry. We're going to start with Lyndon LaRouche. So I need, let's see here. How about, we'll split it in half. So 2 volunteers. So somebody in the room is very welcome. Somebody on Zoom is very welcome. So we'll start with Nancy. If you're on Zoom and you want to read the second half of this excerpt, please raise your hand. On Zoom, are you able to hear Nancy? We're getting some no's. Okay. Well, while we work that out, is there anybody on Zoom who would like to be the first reader? And we'll come back to Nancy as the second. Go ahead and raise your hand. Gretchen's raising her hand. Please raise your Zoom hand. Makes it easier to find you on the list and unmute you. Gretchen, please click the unmute button.
Yeah, just saw it. Sorry, I couldn't find the. All right. And this was all to speed it up. All right. So beginning right in the section that you have on the class statement, right?
Yeah, the
website,
Linux.
right? Reanimating an actual economy. Should I just take it away?
Yes, please read that beginning of that excerpt.
Okay. My included purpose in the immediate project on animations is to demonstrate to intelligent professionals and to others the proper methods of approach and use of computerized animations of country by country data that over periods of 2 or 3 generations, in showing the determining factors in cause of catastrophe or recovery in the U.S. economy in particular today. This work is premised at its first stages on the way in which Johannes Kepler defined cycles within the solar system, and the way in which Kepler thus defined the need for developing both the infinitesimal calculus uniquely developed by Gottfried Leibniz and the successive development of elliptical and higher hypergeometric functions by Gauss, Abel, Riemann et al. The crucial topics treated under that approach include the functionally determined relationship between the general basic economic infrastructure of whole economies and the productivity of agriculture, manufacturing, and rates of tangible, that is, physical growth in the so-called private sector of an economy taken as a unified whole. However, the crucially underlying objective of these studies is to discover the principal factors which are determining or might determine either net growth, decline, or stagnation in the rate of the performance of the economic phase space considered, or a national, give me 1 second to get back up here, in a national or larger economy as a whole. The latter task, the uncovering of the principal determining factor, is the functional requirement essentially lacking in the approach to defining animations in the exemplary case represented by Nordhaus's report. And then an emphasis. The most suitable pedagogical approach to this crucial feature of the study is that modeled on the most essential distinctions of Kepler's reference discovery, the discovery of the principle of the infinitesimal. This is the distinction which is apparently beyond the comprehension of today's commonly encountered academic classroom and related productions, respecting the principles of physical, scientific, and related investigations. Should I pass the baton now, Jason? Or go on?
Yes. Do we have the audio working here?
Okay.
Hold on. Try it.
Can you hear me?
I think so.
Yes. Yes.
Yeah,
Okay.
great.
All right. Kepler and spherics. Knowledge is always essentially subjective because it exists among mortal beings only as human knowledge. Its primary existence lies consequently only within the human individual, and that individual's functional relationship to the history of the society within which he or she lives. Knowledge, in the proper sense of the word, does not exist among lower forms of life. Knowledge is an attribute of that principle of the human individual which sets our species absolutely apart from both inanimate objects and also all lower forms of life. In V.I. Vernadsky's Science of Biogeochemistry, this marks the principle which separates the human individual from the animal. Therefore, subjectively, what has proven itself to be my uniquely successful approach to long-range economic forecasting dates in its origin with me, in my immediate and persisting principled rejection of the standard secondary education in classroom geometry at my first encounter with that subject. My adolescent acquaintance with structures had shown me that the function of geometry in society's practice is physical. Only what is functionally a physical geometry, not a formal Euclidean geometry, could be a valid one. Historically, my standpoint on the subject of geometry, from that moment in secondary education onward, was already implicitly an anti-Euclidean geometry, a view of mine which ultimately converged upon what is to be recognized among the Pythagoreans and Plato as spherics. Spherics was known to those ancient Greeks as a method transmitted to them from the practice of Egyptian astronomy, which distinguished the geometry of the motion of development, for instance, physical action, as distinct from what convention today recognizes as simple classroom versions of so-called Euclidean geometry. So-called a priori definitions, axioms, and postulates are to be excluded from competent European science. All concepts, including concepts of the form of one's own behavior in this practice, are to be discovered by experimental methods associated among ancient Greeks with the tradition of Thales, the Pythagoreans, and Plato. In other words, while we are permitted to take notice of the implied assumptions intrinsic to the practical approach we employ, we cannot treat those assumptions as a priori principles, but only as being themselves subjects of critical experimental treatment. This is the standpoint from which to consider the rudiments of the method employed by Kepler. This is the standpoint plausibly attributed to the work in astronomy of Thales, of Miletus, and is the standpoint of the Aristarchus of Samos, who proved the orbiting of the Earth around the Sun by appropriate experimental methods. Kepler's treatment of the relative positions and motions of solar bodies considered by him can be traced from the starting point referenced by Aristarchus's approach. Also, as Kepler himself emphasized, his own scientific method was derived from the founding of modern physical science as an experimental body of scientific work by Nicholas of Cusa, and as Cusa's initiatives were complemented by the work of such followers of Cusa and predecessors of Kepler as Luca Pacioli and Leonardo da Vinci. That much said, it is sufficient for the purposes of the present report to focus on a narrow but crucial feature of Kepler's discoveries: the implications of the observed Mars orbit in terms of reference to the cyclical alignment of relations among the positions of the Sun, Earth, and Mars. To reduce the matter to essentials, we may say the generation of an elliptical orbit of Mars was recognized by Kepler's measurements to be the result of what Gottfried Leibniz was to make his unique discovery, his definition of the differential or the infinitesimal calculus. Infinitesimal calculus. Simply said, the notion of the infinitesimal, which Kepler presented to future mathematicians, was a reflection of the observed consistency of the fact that the area subtended by the sweep of the orbit of Mars relative to the Sun varied in an ordering of, quote, equal areas swept during equal times, end quote. In other words, the elliptical orbit did not determine the motion of Mars. Rather, the relevant, perfectly infinitesimal principle of physical action generated the elliptical orbit of this specific characteristic, the characteristic of equal areas swept within equal times. Notably, precisely that view of the matter by Kepler prompted him to assign to future mathematicians the development of both an explicitly infinitesimal, right, physical calculus and of a corollary theory of physical elliptical functions. The former challenge was solved by the uniquely original discovery of a calculus of the infinitesimal by Gottfried Leibniz, a quality of the calculus which is rejected in the failed attempt to understand gravitation by Isaac Newton and his followers. The second challenge of discovering the relevant physical principle underlying regular elliptical action was mastered in essentials by Carl F. Gauss and his followers, most notably by the Bernhard Riemann, who followed Gauss in going beyond elliptical functions into higher physical hypergeometries associated with an ontological insight into the matter of the human species' qualitative progress. The actual rudimentary development, the mathematics of a competent mode in modern physical science was derived entirely from the combined effect of these implications of Kepler's discovery with what Gauss was to expose as the implications of what was actually Napier's definition of the pentagramma mirificum and Fermat's experimental demonstration of the existence of physically relative time, the concept of quickest time, as opposed to primitive superstitious belief in simple, for example, Euclidean time. These are the elementary considerations as treated most notably by Leibniz, Gauss, and Riemann, required for the defining of a competent modern science of physical economy. However, in any competent science of economy, there is another crucial aspect to Kepler's uniquely original discovery of universal gravitation. This is what William Nordhaus's treatment overlooks completely. Kepler's discovery of the principled ontological character of the planetary orbit provides students the model of reference for study of economic cycles.
So to give a little bit of context on that, Jose, to get a little bit of context on that, this is a paper that LaRouche wrote it was a guide for some of his young friends on creating animations to understand and convey ideas about economic development. And it's also in response to a paper on geographical economics by Professor William Nordhaus, who had said that basically geography causes economic outcomes, and he was looking to what extent that was true. And Lynn doesn't think that the main cause of economic growth is geography. Let's put it that way. So I'm really happy that we're actually going to touch on I'd say most of the subjects that were just raised in that passage, not today, but in the course of this series. Today, we are going to see how Kepler developed the infinitesimal that was later used by Leibniz to create his calculus. We, next week, are going to be going through Fermat's discovery of quickest time. The week after that, we're going to go through Leibniz's calculus. And the week after that, we're going to get to see how Riemann fits into this, both with Lynn's insistence that you can't begin with axioms and definitions and so forth. You have to begin, everything must be discovered, not assumed. And also, if we have time, on what he said about hypergeometries. So this passage, I think, lays out a lot of what we're going to be getting into. So what I want to do now is I'm actually going to shift to, we're going to watch a video because, well, because it conveys what we need to take a look at. So let me get that. All right, let me get this playing and we'll share my screen. Share sound. It is difficult today to have the opportunity to truly see the splendor of light pollution. In the darkness of a moonless night, the human eye can become sensitive to even very faint light, and the starry sky is wonderfully full. Let your eyes adjust to see the sky of 2,000 years ago. Now, let's have a seat and watch the stars as we talk. During the night, this is what we see. The stars move. Some more, some less, and one hardly at all. It appears just as though we are watching the rotation of a very large sphere around us. We'll watch through the night again, this time with markings to indicate the circles the stars seem to travel upon. Based only on this observation, the simplest explanation is that we are surrounded by a sphere of stars, which move around us just as the sun does. Now we'll turn around and face away from that star that didn't move, and we'll watch the night several times in a row. Each night looks almost the same, but there are differences. See what you can spot. Let me, okay. Well, I'm really sorry about that. I presume you can hear me now. All right. Let me go back then. Let's just take another look at this. All right. I'm sorry about this. So what we had first noticed is that it seems like the stars are moving around us as if they're on a big sphere. It looks like there's a sphere spinning around us. And what we're going to do now is we're going to face away from that one star that was motionless. That is, we're facing south in the northern hemisphere. And I just want you to watch. We're going to go through 1 week of nights. We're going to see, or 1 week of 1 week. See if you can notice anything that's different from day to day. And there's no audio here because that's intended. It's not a problem. If you watch this video in advance and you know what the main thing is that I'm about to point out, see if you can find anything else that's changing from night to night.
It's getting bigger and bigger.
Okay, gee, thanks a lot, guys. Trying to get some new people to weigh in on these kinds of things.
Oh, was that the answer?
Yes.
It just felt kind of obvious.
Okay, well, maybe it was obvious. Okay.
No, but it felt like too obvious. I was like, that can't be.
It's also getting closer and closer to Ryan.
Okay.
Yeah.
Okay, so now we can pose the question, what changed from night to night? So I think a couple people mentioned that the moon was changing. So there was more than one way that the moon was changing. What were two ways that the moon changed?
On the screen also seem to be westward. That's more to the left.
So we just heard from in the room that the moon was getting bigger and was also moving from our vantage point further to the left compared to where the sun was setting and up. Okay. Did anybody notice anything else changing from night to night, day to day?
Phases backwards.
Backwards, and its phases changed. Okay, so that's a good point. The moon moves backwards. Yes, compared to the daily motion of all of the stars and the moon and the sun, those are all moving to the right, and the moon against that seems to be moving the opposite way. So let me ask this, is the moon moving to the left? Is it just not moving as fast to the right as the stars? That it looks to us like the moon is spinning around the Earth every day. It looks like it's spinning around the Earth every day a little slower than the stars. So just from our senses, that's what things look like. But maybe that's not what's happening. So let's take a look now at over a longer period of time. Now, where is my, there it is. Okay, I'm going to share my screen again. Now, on people, maybe please gesture on Zoom. Did you hear anything when I was playing that video before? Was it just that it was quiet for a portion or nothing ever came through? Nothing came through. Okay, great. So I'll just narrate this next video then. That up. Good. So now what let's just watch and we'll see what we observe here. We're going to observe the sunsets over a series of night. Oh, it's paused. That's why. Okay. All right. So we're taking a picture weeks apart at sunset. So here we go. It's the first picture. 1 week later, it looks like this. What happened? So the moon is gone. So what happened between these two pictures? So the first night, yeah, the moon is gone. What else? What else is different? First night to the second night.
To the right.
Do all the stars move to the right? Here. Yeah. So watch a different star and see, let's see if it also moves to the right. Okay. Let's watch one more time. Pick another star.
To the left. No.
Okay, so in case, so first night, second night.
Yeah.
Okay, so yeah, the moon moved to the left. The stars moved to the right. What are they moving to the right with respect to?
No.
Well, yeah, our field of view, but how are we choosing when to take these snapshots? The sun is like the timer for our camera here. So if this,
To me, it looks like the less bright ones move more.
it looks like the less bright ones move more, okay?
Maybe I'm wrong.
So we're going to get a chance to test that out by looking at over many, many nights. If the stars, so first night, second night, let's say that the stars weren't the thing that was changing, but the sun was. If we think of the stars as staying put, which way is the sun moving? From the first one to the next one. Here's, watch it again. First night,
Oh,
second night, right at sunset. Which way is the sun moving? The sun's moving to the left. I mean, left and up, this way.
What do you mean? Imagine if the stars are stationary.
Yeah, like
Yeah, you see east and east and west.
So like imagine this time when think about where the sun is, imagine where the sun is. We can't see it because it's behind the mountain. And the reason it's behind the mountain is if it was up, we couldn't see any stars. So we can only look when the sun sets to figure out what stars it's near. So imagine where the sun is and then take a look at the next week and see if it's any different compared to the stars. Okay. So over day to day or week to week, the sun is moving to the left, like the moon, but slower, right? Margaret pointed out that 1 week later, you couldn't see the moon at all. The moon completely went off the screen. So, okay, there's something in the chat. Let's see. Higher in the sky, days are getting longer. Yes, that's true. The sun was higher in the sky. Good point. Thank you. Yeah, please keep in the chat. That's a good way to share things. So now what we're going to do is we're going to watch over a longer period of time and just see if you notice anything happening here. So this is sunset to sunset, night to night. Oh,
Whoa.
okay. So now what we're going to do is we're going to zoom in on one patch of stars. So when we're trying to figure out how planets or how the moon moves, how the sun moves, you really need a map. And Hipparchus, I'm just going to say roughly 2,000 years ago, I kind of forget where he is exactly, 2,000 years ago published a map of 1,000 stars. And so that gives you kind of a grounding to say where is the moon or where is the sun. So, all right, what we're going to do now is we're going to watch the motion of the sun. There are a series of constellations that the sun is always seen to sunset or have sunrise in. You see the names of those? Leo, Virgo is approaching, Libra, Scorpius, Sagittarius. Are these familiar names? Capricorn, Aquarius. What's the name of, what do we call these constellations? Pisces, Aries. This is the zodiac, right? So that red line that you see here is called the ecliptic. It is the path that the sun takes against the stars. And it seems like that's basically the same every year where that line is. And there's a special name for the 12 constellations on that ecliptic. They're called the zodiac. So the original astrology of what's your sign, that meant where was the sun when you were born? What constellation was it in? So where does it rise in? Yeah. So to review, so during one night, everything's moving to the right. So we're watching over one night. Kepler calls this the first motion. It looks like everything's spinning around us. And then the second motion is keep the stars steady from night to night and see, is there anything moving among the stars? The moon is moving. Overall, most of the stars they're basically staying put. So we can use them as the background instead of the horizon or our viewpoint. We can use the stars as the map to watch the motion of the moon.
Yeah.
Mm-hmm. And this is
stars are static, and it makes it easier to observe the moon.
exactly, gives you a reference point. And the okay, now let's see what comes next.
Static, relatively static compared to.
Yes. What we're going to do now is we're going to zoom in on a patch of the sky, and we're going to watch just that patch from night to night. So we're going to crank up our magnification on our telescope here. And let's see what happens. So these are night to night. Each frame is a day. So is anything happening here?
One star there in the middle is moving.
One star is moving. One star is moving. I thought all the stars stayed put. One star is moving. How about that? I think we get to watch that again here. Let's see. Oh, no, maybe not. Okay, so there was the Greeks gave a name to these stars that wander around, and they called them planets. Planet means wanderer. So the wandering stars. In the book that we're going to read excerpts from, Kepler calls Mars a star for this reason. He doesn't necessarily think it's like the sun, but that's the term that gets used. So now we're going to look over like a long time. What we're doing is we're now focusing on Mars. Mars is that dot in the center of the screen, and each frame is a day. And we got rid of the atmosphere and the horizon and all that. So it's like we're in the space station or something watching this.
Mhm.
Here's what Mars is, huh? All right, it's strange. Here's the sun with a couple other wanderers.
Cool.
Keep watching Mars, moving along. Now, one thing is Mars is staying pretty close to the ecliptic, isn't it? It's staying pretty much on the same path the sun takes.
Mm.
Now, it just twisted again. Was that in the same place as last time? Here, let's do this. Let's watch where this one occurs. What constellation is this in? Gemini. Okay, so let's see if we get to see it again and see if it's still in Gemini.
And what are those stories?
Yeah. So in addition to seeing where Mars stops and goes backwards, oh, here we go. What constellation now? Yeah, there's Gemini, moved ahead to Leo.
It seems like it's going every year. It goes to a preceding horoscope, but it skipped Cancer though.
Yeah, it looked like it jumped about 2.
Yeah.
Now, the other thing is, when is it moving at its fastest? We saw when it stops and loops. Any hypotheses, or just let's watch it again and see if you can, oh, there it goes again. So from Leo, now we're in Virgo. And let's see, when does it move its fastest? Be kind of blur your eyes and just watch the stars. When are they moving the fastest behind Mars? Oh.
When it's close.
There's a few, okay, so there's a few different things there's a few different motions.
There's other stars seem to be moving really quick when it's closer to the sun.
The other star, Harry says the other stars seem to be moving quick when Mars is near the sun. And yes,
Other stars are closer to the sun.
when the other stars are close to the sun.
Anyways,
Oh, yeah. So when we see the sun, it's because since we're focused on Mars,
Yeah.
it's when Mars is near the sun.
we know when Mars moves the fastest.
So let's see here. A few comments came in on the chat. Let me just read some of these. We have, oh, it's very nice. I thought about the allegory of the cave, and what if what our eyes are seeing no longer exist? Are we seeing a shadow of the stars?
It's actually about
Isn't that interesting?
It takes time for
We got the, Hugo says the ecliptic is the projection of the Earth's orbital plane around the sun. So Hugo is saying the ecliptic isn't the sun moving through the stars. It has something to do with our moving. So I think we haven't seen enough yet to really know whether everything's moving around us or if we're the ones doing the moving. I mean, if we go with observations, does anyone feel the Earth moving?
No, it's absolutely solid. It doesn't go anywhere.
Besides earthquakes, the Earth is, it's basically feels like it's staying put. All right. Samantha says Mars is in retrograde sometimes. Yep, that's the term that gets used for it. Retrograde, going backwards. Sarah, is that Mars in retrograde? Yes, it is. It looped. Mars's orbit is tilted about 3 degrees with respect to the ecliptic, says Ugo. I'm not sure, Ugo, if that came from looking up something or was that your estimate from watching just watching the visuals? And Mary Jane in the chat says Mars is moving fastest when it is close to the sun, which is accurate. So every time Mars went backward, the sun wasn't on the screen. Should we see that again? Maybe we should just watch that one more time. All right, let's get that up again. Okay. Okay. So, oh, yeah, okay. In fact, oh, I've got an idea. Let's actually do this. Let's count maybe out louder to yourself, or let's count together how long it takes from when the sun reaches Mars to when the sun reaches Mars again. How many seconds it takes. All right, here we go. So, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 11, 12, 13, 14, 15, 16. Now, does anyone remember what number we were at when it went backwards?
8.
About 8, 8, 9. Yeah. So halfway through the sun coming back to Mars is when Mars moved backwards. So that's when the sun is on the opposite side. Mars only does this thing of going backwards when it's most visible at like midnight, in the middle of the night. If Mars is near the horizon when you see it, I'm sorry, if Mars is near the sun when it sets or near the sun when it rises, it's never going backward. The only when we see it going backward is when it's opposite the sun. So you might think about, just please think about why that might, in your mind, why that might be. Why would Mars go backwards only when it's not near the sun? Okay, so what we're going to do now is we are going to take a look at some of the explanations that were, I see the camera's sliding down. We're going to take a look at some of the explanations that were given in before Kepler came onto the scene about why this occurred. Why does Mars go backwards some of the time? And we're going to start with a guy named Claudius Ptolemy. He wrote a book called, let me share my screen. He wrote a book called it's called the Almagest usually. That means the greatest in Arabic, and so I prefer to call it by its original Greek name, Syntaxis. Anyway, Ptolemy wrote the Syntaxis in 150. And this is what he said. He said, okay, the Earth does not move. The sun moves around the Earth. Mars moves around the Earth. But in order to make Mars do that backwards looping, he said Mars moves on a circle on a circle. So at first there's that red circle centered on the Earth. That's called Mars's deferent, is the word Ptolemy used. And that circle on top of it, does anyone know what that circle is called?
Sorry, there's too many circles.
Yeah.
Okay. All right, let me see. I don't think it's possible to pause, I'm afraid. So, okay, so this red dot right here that's moving is on a circle that's called the deferent. And it's going around the Earth.
Yeah, Mars.
Now Mars is over here. Here's Mars. It's moving on another circle,
Yeah.
which is called an epicycle.
Yeah.
So, Ptolemy definitely said, okay, definitely circles. That's how things are going to be moving. Circles, not squares or anything like that. Circles. But since Mars obviously doesn't just move the same speed from night to night, and it sometimes goes backwards, and it always goes backwards when it's away from the sun, let's watch that happen here. So the lines coming out of the Earth are where do we see the sun and Mars? So watch for when Earth sees Mars going backwards. Overall, Earth sees Mars moving to the left, counterclockwise. Let's watch for when we see Mars go the other way. Yep, there it did it, and it was opposite the sun. Now, is there anything that you notice that's similar between the sun moving around the Earth and Mars moving around its deferent point? Any similarities there at all?
They're parallel.
They're pointing the exact same way. So that's kind of suggesting that the sun has something to do with how Mars is moving. Um, but anyway, Ptolemy said, well, that's just a very interesting coincidence. Everything goes around the Earth. The Earth is the foundation of everything. Now, this next guy, I'm sure you've heard of, Copernicus. He was the first modern to write a book that really gave a model that mostly put the sun in the center. He didn't really, but he put it very close to it.
It was not like an evolution, like the first model that had the sun.
Yeah, it was the first like really quantitative model. So Linnad said that Aristarchus in ancient Greece said that the Earth goes around the sun. Copernicus is the first published model with like parameters and numbers to be able to say, hey, in 2 months, where will I see Mars? Copernicus let you calculate it, and he said the sun is stationary. The Earth is moving.
Oh.
So now watch the direction from the Earth that we see Mars. And look, from the Earth's point of view, it's moving counterclockwise, 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 whoop, clockwise, counterclockwise again. So watch it again. So think about how Copernicus explains Mars going backwards. In this case, is Mars moving backwards? Is it changing its direction?
Jose, you have to shave your head.
Yeah, just the Earth is overtaking it.
The Earth is overtaking it. Yeah. So the backwards motion, according to Copernicus, there's nothing moving backwards. We're overtaking it. We're running faster than it. And when we pass it on the track, it looks like it's going backwards. What do you think about this? Does this seem like a better model? Let's see, our questions come in. The Earth does move. I measure it in the summer. Okay. How did he justify that? Says Samantha. And since I didn't see this in time, I'm not sure if you're asking about Ptolemy or Copernicus.
Ptolemy.
Probably Ptolemy. Okay. How did Ptolemy justify this? Great question. Can anyone out here, can we help him? Can we come up with what kind of answer might Ptolemy have given for why this would make sense?
Works.
It works. That's a great answer. And I think that's basically what Ptolemy said. Hey, you want to know where the planet is? I got you covered. Does it make sense? That's kind of a different question. Okay.
He was able to predict like
It's with this thing.
Yeah, exactly. Yeah, that picture. Yeah. So he was able to predict things. So he said, well, if you've got a better idea, put it in practice. Otherwise, I've got the best numbers, so I'm right. So now Copernicus did give some justification for why he thought the sun should be at the center. But let me actually switch to, okay, from the Earth, it appears that everything moves around us. Let me switch to another quote from our reading packet. And I'd like to ask if anyone on Zoom would be willing to read this very short passage from the Syntaxis. This is Ptolemy explaining why the Earth cannot spin. So if anyone on Zoom would like to raise your hand to read this short passage, please. Sarah, okay. Please unmute and go for it.
Okay. For us to grant these things, that the Earth rotates on its axis every day, they would have to admit that the Earth's turning is the swiftest of absolutely all the movements about it because of its making so great a revolution in a short time, so that all those things that were not at rest on the Earth would seem to have a movement contrary to it, and never would a cloud be seen to move toward the east, nor anything else that flew or was thrown into the air. For the Earth would always outstrip them in its eastward motion, so that all bodies would seem to be left behind and to move towards the west. Sorry, am I supposed to go on?
Sarah, would you, so in your own words, putting you on the spot here, I know, How would you, what's Ptolemy saying? Well, what's his reason that the Earth can't be spinning?
I would really like to answer that question, but I was focused more on how I was reading than what I was reading.
That happens. That happens. Okay. Um, would anyone in the room like to restate it in plain English? Well, here, let's let Nick take a turn.
Yeah, so he's saying
Because if the Earth is rotating, it has to be really fast to go.
all the way around once. So say you throw a ball up in the air, you'd keep moving on the Earth and the ball would seem to go the other way.
And the cloud
Would never be seen to be moving. They would always be going west.
is if the Earth
Is turning east, they would not keep up with the rotation of the Earth.
they would
They
have
would
to go
go
west.
west.
Right, right. If you threw a ball up, the Earth would spin in the meantime and it would land somewhere else. And that doesn't happen, so the Earth doesn't move.
Why do you say the Earth has to be moving so fast?
Well, the question was, why would he be talking about the Earth moving so fast? He's saying that if the Earth spins around once every day, that would be such a fast motion. Of course, he's fine with all the stars spinning around every day. Okay, go figure. But he says the Earth, oh, that's way too fast. Basically, he's saying if it was moving that fast, we would have noticed.
I agree.
Because given the idea about how big the Earth is, if it had to spin all the way around once every day, I mean, how many miles an hour is that?
You mean spin around the sun?
No, spin around its axis. Yeah, he also gave an explanation of why the Earth. Okay, so good point. Ptolemy said two things. He said the Earth definitely doesn't move around the sun or anything else. Similar reason. He said, well, then if a bird started flying, the Earth would, be moving around the solar system, and then the bird would be, left out in space, basically. And what we read was his reasoning for why it also can't spin. Because some people would say, okay, but can it spin? I mean, everything looks like it's going around us. It would be easier if we just did the spinning and the stars weren't moving. And this is why he says, nope, 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 nope. We're stationary. We never move.
Let me ask you, was Ptolemy was much later than Eratosthenes,
I believe so.
so he must have known about
These.
experiment and measurement of the size of the
Yeah, Ptolemy would have had an idea about how big the Earth is. That's right.
He's assuming that means something that big couldn't be spinning that fast.
Yeah, that's what he's saying. I mean, what is the equator? Does anyone know how many miles or kilometers around the 25,000? So 25,000 miles or kilometers.
Wow.
So 25,000 miles, 24 hours in a day. That's about 1,000 miles every hour. So you'd think you'd notice that, right? There are some hands. Okay, let's see. Nancy and then Samantha. Nancy, please unmute. Nancy, I can't unmute you. You need to press the unmute button now. Okay, Nancy, you were unmuted, but we can't hear you. Okay, we're going to Samantha.
Okay, so I have a question. Is Ptolemy a mathematician? Is he basing this on observations, things that he sees, or is he basing it on calculations that he's made? That's my question.
Well, it's a little bit of both. So Ptolemy has observations that he's made. He actually, did look at the stars, the planets. So he has some data. He's not just completely making up numbers. He's got something that he's going on. But then he's made a theory. He's made a hypothesis. So he's saying, okay, here's the observations. Where'd they come from? Oh, a circle on a circle. And the whole thing's spinning every day on top of that, which I didn't include in that earlier picture, right? That picture really should have also been spinning incredibly rapidly to get the daily motion. So he could test his idea by using the parameters of his model, what angle this is at, how big this is, how fast the epicycle spins, how long it takes Mars to go around the Earth. And he could put all that together and then say, okay, I can predict that in 6 months, Mars will be, about halfway through Aries, some specific prediction. And then you could test it and see if he was right or not. He wasn't that accurate. He could be off by multiple degrees, but that was still considered the best that was available at the time. Does that address what you were wondering, Samantha?
Yes, it does. Thank you. I was wondering if he had specific mathematical equations. So yeah, that pretty much covers it. Thank you.
Gene, feel free to unmute.
Hi, thank you. I have a couple of questions. The first is, what will they think about the size of the planets that we're looking at, like the red planet and stuff, and the galaxies that we're looking at right now, which is a different universe that we thought of a couple of years ago. The other question is, we're missing the global south look at the stars that and their knowledge and their ideas by just looking at the North Pole. And in my opinion, they had to had previous ancient knowledge as well, because the Mayas and other cultures were able to have very good astronomers as well. So I think we're just we have more things to think about it.
Well, thank you for that. I mean, that is true. The astronomical tradition that we're following here is what leads into Kepler. And in his day, he didn't know anything about Mayan civilization. But it goes to show you something universal about human culture, that, you know, everyone on Earth can see the stars. Everyone on Earth can wonder what's happening. Everyone on Earth can notice the changing seasons and try and say, it would sure be good if we could know when this would happen. That would really help us plan. So astronomy developed independently in many places on the Earth, and that's true. So we're focusing on the train that leads into Kepler, because he's the main focus of this presentation. But you're right, this is not the only discovery of some of these cycles. Speaking about the old, or how some of these would have been ancient observations, you know, the Egyptians, Hipparchus, okay, so every 26,000 years, the whole, so you remember I said that the sun rises in a constellation and that's your sign in the zodiac? Well, over time, the same day of the year, the sun keeps moving, excuse me, on the first day of spring, the sun used to rise in the first star of Aries in like around 2,000 years ago, but it's moving. And over 26,000 years, every position on the ecliptic will be where the sun rises on the first day of spring. The reason I'm bringing that up is 26,000 years is a really long time. And Hipparchus figured out, I'm not sure quite how accurate he was, but he figured out that this cycle occurred and gave some estimate of how long it would take for this to happen. There's no way he could have done that without knowledge from the Egyptians. So, you know, you want to talk about a long tradition over, you know, hundreds of years of taking observations. Some of these things, you can only do it if you have a continuous civilization, or, you know, civilizations in contact over a really long time. So it's a shared endeavor.
That underscores the importance of having collaboration on the sciences, make sure it does continue.
Right. So we should collaborate internationally today. Although scientists trying to come to the US right now are, you know, sent to El Salvador or something instead. So it's
also
pretty stupid.
I want to agree.
And then let me just answer the other. And then you'd also brought up, what did they think the planets were? The Ptolemy, Copernicus, they basically thought that they were stars. They were like the stars. So I don't really know what they thought they were, but the planets were essentially similar to those, just that they moved, is my take on it. All of this, including Kepler, is before the telescope. So, well, actually, the telescope came during Kepler's life, but by the time the book that we're going to be looking at, there was no telescope. So the idea of actually seeing the size of a planet or seeing that it looks like a round thing, like the moon, no one had seen that yet. And Art?
Yeah. Sky map of the thing circling around Polaris, right? In this 26,000-year cycle, that star that seems to be at the center changes. 6,000 years ago was the star Vega.
Mm-hmm.
So by the time the earliest pyramids were being built, Vega would be the one that would be going around.
Mm. Yes, just to make sure everyone heard oh yeah, we need to get better at switching the mics. I'm sorry. Well, Mary Jane said she couldn't hear him, so I don't know. I'm just oh, you're right. Okay. All right. So, all right. Yeah, Art was saying that when we saw before that one star that wasn't moving, the North Star, that's Polaris. But he said that at the time of the construction of the pyramids in Giza, that star was Vega, was the one that doesn't move. And so, yes, this is the same 26,000 year cycle. It's also which star is the North Star. And then to go back to what Eugene had brought up, that there are different constellations visible in the southern hemisphere. That's true. And there's not really one star at present. There is no south star right now.
Yeah.
You have to sort of look at a few stars and draw a line between them to get due south. But I will say that everyone on the Earth shares the same ecliptic. Because those constellations are visible wherever you are. I mean, unless you're on the North Pole, I guess. But you know, they're well, even then, they're visible to everyone on Earth. So that is the moon and the zodiac. These are common to all human beings. Okay, so let's move ahead now. So we talked about Copernicus. Let me switch over to show one more thing. All right, so that was Copernicus. Now, Tycho Brahe, the reason to bring him up, he's not really well known today, but he was a Danish nobleman. He was filthy rich, let's say. And he had his own island, and he built what was the world's greatest astronomical center in his day. He had, this is before telescopes, but he had extremely large pieces of equipment to try to measure very precisely where the stars were, where the planets were, where the moon was, where the sun was. He had a big staff so that every night, you know, multiple staff members could measure where something was, and they could combine and take an average of their observations. So putting this all together, Tycho Brahe had fantastic data. I was at a conference in Prague in 2009, and some of the people there had taken Tycho Brahe's recorded observations and sort of recreated them with a stellarium kind of program to recreate what is it really. And he was within a minute or two. A minute is a 60th of a degree. So think about a protractor, how big a degree is. Small. Tycho Brahe was looking at about 1/30th to 1/60th of a degree. Pretty fantastic.
And there are seconds too,
And there's seconds, second minutes. Yep. So Tycho said that the planets, like Mars, move around the sun. So here you got the sun and Mars moving around it. Very nice. But he said the sun, with all the planets, moved around the Earth. So this seems like perhaps it's a step backward. But this also, I mean, partly it avoided any controversy with the church about the Earth moving and so forth. Kepler, one of the first things translated into English of Kepler and made widely available actually was his commentary on people quoting the Bible to say that the Earth doesn't move. And he said, look, you know, in this case, the Bible is trying to present us with it, you know, it's a divine messenger. Don't bring it into physics class. This was a metaphor. I mean, really, okay? Like there's some biblical story about where the sun didn't set, that, you know, God kept the sun up longer. And Kepler's like, look, the point was just to make the day longer. I mean, the Bible doesn't mean that the God didn't stop the Earth from spinning and definitely stopped the sun from moving. Just the point was he made the day longer. Please don't be so literal here. So that's these three guys' models. Now, the thing is that they seem pretty different. Right, those three models, I would say. But the first thing that Kepler does in the New Astronomy, which is the book that we're going to be focusing on when we start getting some more into it here, he said, okay, how do I determine which of these three is right? Is Ptolemy right? Is Copernicus right? Is Tycho Brahe right? His boss? Kepler thought that Copernicus was right. He was definitely a Copernican. He said that's the sun, the sun is what stays put. But the first thing he actually does is he says that you really can't tell them apart. So we'll see that here. This is unfortunately, when I made this, and I can't change it now, the eccentricities are so big that it looks like the sun is touching Mars's deferent. And anyway, this is a rough idea of the Ptolemy system. So here's the Earth. This is the center of the sun's orbit. The sun moves in a circle around the center. This deferent point of Mars itself speeds up and slows down. See if you can notice when it's going faster or slower. Focus just on this small dark red point.
It goes faster.
Faster down here. Yep. So that's interesting. Now, Copernicus's model looks a little bit different. I had said before that Copernicus sort of put the sun at the center. He doesn't. When he's determining Mars's orbit and the center of Mars's orbit, this is the center of the orbit of the red planet. He measures it with respect not to the sun, but the center of the Earth's orbit. Copernicus was still essentially using the Earth as the center of the universe. The sun itself really doesn't come into any of his models or calculations about the other planets. Anyway, they seem a little bit, these obviously look different. And then Tycho's looks different from the others. So here, again, with Tycho, you have the sun, and it's not really the sun that Mars's orbit, stop it. It's not the sun that Mars's orbit is attached to, but an imaginary point near the sun that is really where it would be if it went in a circle around the Earth instead of being off-center from the Earth. This might be a little too much detail. Now, the thing is that really all three of these they're completely equivalent. So watch this. I can go from Ptolemy's model to Brahe's model. None of the planets move. You're really just changing the geometry of it. Now, let's turn on the orbits, the shape of the orbit. So this is the path that Mars takes according to Ptolemy. And as I move to the Tycho Brahe's model, it doesn't change at all. The exact same path of Mars through the solar system, no difference. Now going to Copernicus, the overall path does differ, but again, maybe just watch the motion here. Let me turn the orbit off. Okay, Copernicus, Tycho. You're really just moving the camera. Or is the camera focused on the Earth? Is the camera focused on the sun? In fact, you could just say, well, let's say that it's the midpoint between the sun and the Earth that's the center of everything. You could do that if you wanted to. You could say that the Earth and the sun are both orbiting this imaginary point. Right? So Kepler's point is that basically you're not going to be able to answer who is right from observations. How are we going to figure out whether it's the Earth that moves? Can we? So there's one thing he finds that is not equal. So let me show that now. So I'd mentioned that Copernicus is using not the sun itself, but the center of the Earth's orbit to set up Mars's orbit. Kepler says, no, we should use the sun itself. And the difference between using what's called the mean sun and the real sun, called the apparent sun, this does make a definitely observable difference in terms of where you would see the planets. Definitely does. So here, let's just stop right here. Oh, yeah, sure. Oh, yeah, so take a look at this conjunction right here. Sun, Earth, Mars, all in a line, basically. As I switch between using the mean Earth, a mean Sun, and the apparent Sun, take a look at this diagram in the bottom right. This is where we see Mars. This is a little exaggerated, but it was over a degree. So Kepler's saying, okay, that's something we can actually find out. That's something we can answer. Maybe it's much better to use the actual sun.
Yeah.
Yes.
So Copernicus did not put the sun at the actual center of the Earth's orbit.
No.
Why?
Because of the different lengths of the seasons. So the Earth definitely can't go directly around the sun. The thing I was getting at wasn't, yeah. So
he took that into consideration then and said, okay, it's slightly off.
Right, and this is why also Ptolemy didn't say that the sun goes right around the Earth. It has to be offset a little bit because the seasons have different lengths. The thing that Copernicus did that Kepler was very disappointed in is that when Copernicus said, here's the sun, here's the Earth's orbit's over here, instead of using the sun, he used the center of the Earth's orbit when measuring all the other planetary orbits.
But all are circle.
Yeah, he used all circles. Yeah, yeah. Everybody used, that's one thing they all agreed on, circles. They like circles. All right, so now I want to go through what Kepler did to test out the, to test out whether you should use the real sun or not. Now, at this point, I want to point out what kind of observations we should be making. When we were watching the Mars before, and it was, you know, moving sometimes forward, sometimes backwards, were we seeing where Mars is from some universal vantage point, or what's the limitation of any observation of Mars that we make from here?
Seeing it with respect to the background.
We see it with respect to the background of the stars, okay?
Seeing it from Earth.
We're seeing it from Earth. So every observation you make, the motion of the Earth is tied up in where you see Mars. So it's how do you separate those and watch Mars from the sun? Well, that's what Copernicus, actually all of the guys did this in some way. So here we have a lovely animated GIF. So every about 780 days, the Earth, Sun, and Mars line up. Mars is at its peak right at midnight when the sun is exactly opposite the Earth. So if you have these observations, you can watch Mars from the sun. And if you think the sun is the, you know, unmoving, you know, reference point for everything, as Kepler does, this is really helpful. Now, because you can only make these observations once every a little bit more than 2 years, there aren't a lot. So Kepler had from Tycho Brahe, who was his boss, and from his own observations, he only had 12 of these. That's it. 12 observations. That's all he's got to be able to work with.
That's 24 years worth of observations.
It's, yeah, that would be roughly 24, maybe a little longer years of observations. Yeah, it takes a long time. Takes a long time. Now, the way I do have to show one more thing. I know there's a lot of detail here, but it's required. So in addition to believing that everything was a circle, okay, let's do this. You might just say that Mars, oh, you know, this is really what Adrian's going to be doing. Okay, I'm just going to give the short version of this then. This is what they said. They said, does this do it? Okay. Here is the center of the orbit. Here's the sun, which is not at the center of the orbit of, let's say, Mars. And there's this blue point. This is the equant. This was invented by Ptolemy to make Mars speed up and slow down in addition to the epicycle, that deferent point also it speeds up and slows down. He did it by saying there's an imaginary point that if you watched Mars from this point, it always goes the same speed. So this blue line coming out of the blue point, it's like a clock going counterclockwise, constant speed. But Mars itself seems to speed up and slow down. So these are the assumptions coming into to Kepler. So now let's see what Kepler did to try. The first thing he does is he actually uses the assumptions of his predecessors. He says, let's go with this and let's see how good it can be. So I'll show the picture of this here now. Okay. Now, all right, what we're seeing here, the red positions, sorry, these I can't point without here. Okay, the red lines are the locations Mars was seen from the sun. So in other words, so this line, the sun sees Mars in a certain direction. That's the red lines here. The blue lines represent when we made that observation. So between these two observations here and then here, here's how far Mars moved, that angle around the red point. Here's how long it took, the angle around the blue point. The time when Mars goes backwards is not always exactly the same. It varies a bit. So here, did Mars... Okay, let's just keep going. Here's how Ptolemy had sort of fiddled with this. He said, look, the center of the orbit, there's only one place so we can put the center of the orbit so that it's right between the equant and the sun, well, the Earth, and results in a circular orbit. We start with the red directions, that's where we see the sun. We start with the blue, the angle between the blue points, that's the time between the observations. So what we need to figure out is the orientation here. You can see I'm rotating the blue. You know, we have to orient the equant, and we got to figure out where, you know, what direction against what star, what constellation should we put it. And so there we go. That's what Ptolemy did, essentially. Kepler said, well, you know what? I'm not going to assume that the center in black has to be midway between the blue equant and the red sun. So he used 4 observations, and it's like a hard game or something. He used 4 observations, and he worked out the best that he could get orbital parameters. So Kepler said, you know what? The center of the orbit is further from the sun, and it's a little bit closer to the equant. And he called this, this is like exactly what he made. This is his, he called it a vicarious hypothesis. When he tested it out against, he used 4 observations to make the model, and then he was able to use the remaining 8 to test it. It worked great. For most of the other observations, the difference between the observation and the model was under 1 minute. In other words, perfect as far as you can tell, because Tycho's observations were only good to within a minute or 2. The largest difference was 2 minutes and 12 seconds. So in this, oh, hold on. I just need to see if I make sure I'm not missing anything from the chat here. Why was Kepler obsessed with Mars? That's a good question.
You wrote a chapter about
Huh?
You wrote a chapter about how I came to study Mars.
Yeah. Well, partly it was chance, but it was really fortuitous chance. So Kepler got a job with Tycho Brahe. Tycho Brahe was the imperial mathematician for the Holy Roman Empire. He was in charge of all of this. And when Kepler showed up for work, Tycho said, "You're in the Mars group." And he put him in the Mars group. And Kepler later said, "Boy, I'm really fortunate that I wound up looking at Mars, because Mars, it's different enough from a plane circle that you could actually figure out that there's a different cause involved. If he had Venus, he maybe never would have made his discovery, because Venus it's not that different from just a normal circle. So partly it was chance. But as he saw it, perhaps it was divine providence giving him the opportunity to know God's thoughts better. And that's the way Kepler thought about these things. Okay, so because this vicarious hypothesis worked so fantastically, it did two things. One is it showed that using the real sun is way better than using the non-real sun. Kepler's model was much better than Tycho Brahe's. It was much better than Copernicus's. It was much better than Ptolemy's. It was more accurate. In fact, it was so accurate that you couldn't say that it was wrong. The observations wouldn't tell you that it's wrong. But there was one misgiving. Well, let me focus on one of his misgivings on this. Not misgivings. One of the problems that he posed to this hypothesis. He calls it his vicarious hypothesis, which is kind of a weird word. A vicarious hypothesis. The reason he calls it that is he doesn't believe the E-quant is real. He thinks this is a made-up nonsense. So let's, now here's what he noticed. These two distances are different, right? Sun to center, center to equant. Well, this sun to center distance, he didn't measure it directly by ever measuring how far Mars was from the sun. It only came from being what would work to explain where Mars was along the ecliptic, what constellation it was in. Kepler then added not just the motion along the ecliptic, but then he looked at how far Mars would go above or below the ecliptic. And when he did that, he did not get the same number. When he actually measured the distance, he said, well, the center really should be right between the red one and the blue one. It should be right in the middle.
Where the green one is?
The green one's not right in the middle. He said it seems like just from directly measuring the red-green distance, the green point ought to be about here. It ought to be right in the middle. Like Ptolemy said, it has to be right in the middle. So Kepler kind of tongue-in-cheek says, well, I guess Ptolemy was very smart. He knew that, huh? But when you move it, when you move the green point to be right in the middle, it's no longer perfectly accurate.
Yeah.
It can be off by up to 8 minutes. And I would like somebody to read from the handout on page 7 out of 8 on the handout. There is a quote from page 211. Actually, there's 2 of them. So I do like giving an opportunity to people on Zoom who are mostly just typing. Zoom, if you would like to read this quote, you have a few seconds to raise your hand before we go to the room.
If you do go to the room,
Joe Jennings.
if you do go to the room in the future, just make
Mute myself. Yes. All right. Joe, go for it. Joe Jennings.
Okay, you want me to start at 211 now, correct?
Yes, please read the first quote from 211.
Okay, and from this difference of 8 minutes, so small as it is, the reason is clear why Ptolemy, when he made use of bisection, was satisfied with a fixed equalizing point. For if the eccentricity of the equant, whose magnitude the very large equations in the middle longitudes fix indubitably be bisected, you see that the very greatest error from the observation reaches 8 minutes, eight
Minutes.
8 minutes. And this is Mars, which has the greatest eccentricity. It is therefore less for the rest. Now, Ptolemy professes not to go below 10 minutes or the sixth part of a degree in his observation. The uncertainty, or as they say, the latitude of the observations, therefore, exceeds the error in this Ptolemaic computation.
And Joe, would you like to put that in your own words?
Well, I mean, he determines that there's unacceptable discrepancy in the models, but no, I can't really go much further than that in terms of my own words.
Okay, so there is an unacceptable discrepancy in the model. Yeah, Kepler is not okay with this, but in this quote, he hasn't really weighed in to say this is too bad. He pointed out that Ptolemy doesn't even try to be better than within 10 minutes. So if the biggest error is 8 minutes, maybe it's not a big deal. But let's see, could anyone read the second quote from page 211? And I'm sorry, I shouldn't always put readers on the spot and ask them to put it in their own words. So if that's holding you back from raising your hand, I promise I won't do that anymore. Okay, here, Diane Sayre. Okay.
Hi. Can you hear me okay?
Yep, go ahead.
Okay, good. Since the divine benevolence has vouchsafed us, Tycho Brahe, a most diligent observer from whose observations the 8 minutes error of this Ptolemaic computation is shown in Mars, it is fitting that we with thankful mind both acknowledge and honor this favor of God. For if I had thought I could ignore 8 minutes of longitude in bisecting the eccentricity, I would already have made enough of a correction in the hypothesis found in chapter 16. Now, because they could not be ignored, these 8 minutes alone will have led the way to the reformation of all of astronomy and have become the material for a great part of the present work.
So what does that mean, Diane?
Well, he seems to be saying that that the divine benevolence gave us Tycho Brahe, which gave us observations in 8 minutes of error. We should be thankful and honor these 8 minutes of error because for Kepler, they were not acceptable. And he went on to discover a much more truthful principle. So he said these 8 minutes alone will have led the way to the reformation of all of astronomy.
Thank you. Okay, so now, hey, Adrian, what do you think? Okay, all right, so now we're gonna, camera please, I'm gonna pose a question and Adrian's gonna take us through something, which is this question. What if Kepler's vicarious hypothesis didn't break down? Oops. Hold on, I need to, there it is. What if Kepler's hypothesis didn't break down? What if the vicarious hypothesis didn't break down? What if there was no 8 minutes? What if Tycho Brahe's observations weren't available? If Kepler couldn't prove that this hypothesis using a circle and an equant was wrong, does that mean that it has to be accepted? Is being consistent with observations all that's required to be true? So Adrian's gonna take us on a tour of this. Yeah, sure. I'll start with the screen shared or.
Yep.
Okay.
Thank you, Jason. Yeah, so
Yeah, I mean the question really gets back to um, the what. Sorry, let me just full screen this. What Kepler is looking at is this question of how how the ancients, Ptolemy, his predecessors, Ptolemy, Copernicus, Brahe, how they had these ideas that turned out to be incorrect, but they managed to dig themselves down this tunnel or into this cave perhaps and made themselves believe that they were pursuing the truth. And he actually names chapter 21 of his book, Why and to What Extent May a False Hypothesis Yield the Truth? So I know a lot of you guys are probably going to be familiar with this presentation, so I want to just like go through it so we can get to maybe have some back and forth. But yeah, what he's really getting at is the question of where did these previous hypotheses come from? How did, Jason was showing us this graphic of the Ptolemaic system. Where did Ptolemy exactly come up with all this, these deferents and these epicycles and everything, and the stationary Earth? And he begins chapter 21 with this quote. I'll just read it. It's a fairly short quote I have here. The fact that the result appears identical to the senses does not prove that the as yet unknown true hypothesis and the false one assumed by us have an identical result, for they can be a very small discrepancy which the senses do not perceive. There are, however, occasions upon which a false hypothesis can simulate truth within the limits of observational precision with respect to the longitude. These I shall not demonstrate. So he's getting at, first of all, he's getting at this idea that Ptolemy, his instrumentation only had a certain level of precision. So if you know that your observations could be off by as much as 10 minutes, then you could come up with something like the vicarious hypothesis, and you could say, well, it's close enough. So therefore, I'm just going to go with this. It must be true, right? The other thing to note is what happens when you're only looking at a small amount of data and then you expand the data set that you're looking at. So here I have a graphic of what you might call a Ptolemaic model of a uniform, or this is more of a Copernican model of a uniform circular orbit around the sun. And actually, Martin, could you pass me the packet there? The top one, just the top. Yeah, thank you. And so could I actually get a reader for, sorry, if you turn back a page in the packet, there's a fairly lengthy quote from pages 184 to 185. I just want to go through, I think just the first paragraph will do, to sort of illustrate what we're getting at here. Anyone from the room want to read? Sure.
Mute and then
Unmuted, and then kill the audio there, and then I'll bring this back here. Go for it.
So this is part 2, the first inequality in imitation of the ancients. Ptolemy, in book 9, chapter 4 of the great work, the Almagestor Syntaxis, where he's about to take up the first inequality, made by way of preface, a somewhat cursory declaration of the suppositions of which he wished to make use. It is, in summary, as follows. We see that a planet spends unequal times on opposite semicircles, as although from 2 2/3 Cancer through Leo to 26 3/4 degrees, 2 2/3 degrees Cancer through Leo to 26 3/4 degrees Sagittarius is less than a semicircle, and from 26 degrees Sagittarius through Aquarius to Cancer is more than a semicircle. Nonetheless, the planet is found to spend longer on the former than on the latter, although a law of uniformity would require the contrary. From a mean longitude of, I guess, 2 south 23 degrees 18 minutes. Two signs. Mean longitude of 2 signs 23 degrees 18 minutes to 9 signs 5 degrees 44 minutes is 6 signs, 12 degrees, 26 minutes, more than a semicircle. That is more than half of the planet's periodic time. So from 12 degrees, 16 minutes, Pisces through Leo, to 12 degrees, 27 minutes, Virgo, is about a semicircle in 11 minutes. But if the mean longitude of the former position, which is 11 sign, 9 degrees, 55 minutes, be subtracted from the longitude of the latter, 5 signs, 14 degrees, 59 minutes, the difference is seen to be 6 signs, 5 degrees, 5 minutes, which is 5 degrees, 5 minutes more than half. The planet consequently takes a proportionally shorter time from Virgo through Aquarius to Pisces. Now, if you examine adjacent positions one at a time and compare the intervening arcs with the times or with the arcs of mean longitude, you will see that the planet is slowest at one fixed point on the zodiac and swiftest at the opposite point, and that at the intermediate points, its motion gradually increases or decreases according to its proximity to one or the other. These things reveal, first of all, okay.
Yeah, thank you. So yeah, there's a lot we could get into. I also just wanted to kind of give people a sense of what it's actually like to read Kepler, because it can be a bit of a yeah, challenge. But so what he's pointing out is that Jason was talking about how there are sort of two anomalies that we have to grapple with if we want to model the motion of the planets. And the astronomers call them the first inequality and the second inequality. The first is, as we noted, the irregular, which he's talking about here, the fact that Mars's motion around the Earth or around the sun is irregular. So it speeds up sometimes and slows down. And that's what I've tried to depict here on the right, where we have two sets of rings. On the inner ring is data from two of Tycho's observations, 2 data points. And then on the outer ring is basically, if we were to say that we're going to predict the first observation perfectly, which is this blue line and the two planets here lining up, then when would we predict where would we predict the planet to be at the time of the second observation? So we see that if we insist on having a uniform circular orbit, that's our model, that we can predict one observation correctly. But if we just add a second observation, we're going to predict at the time of that observation, we're going to predict that it's significantly further along than it actually is. And that is enough to prove that the motion of the planet is irregular, is non-uniform. So that's the problem that these astronomers were confronted with, as they could see that the motion was non-regular, non-uniform. So how do you deal with that? How do you come up with a model that can take that into account? And I think I'll sort of give my own take on it, and sort of giving some of Kepler's ideas perhaps in my own words, which is that they sort of just took they were a bit lazy, and they just wanted to fix the model, just make a quick fix in the easiest possible way. So they said, instead of having the planet orbit around the sun, we'll just have the planet orbit around an imaginary point near the sun. And I put a question mark here because we don't know what's there. But the idea is that if we allow this point to move around and we can just drag this around, then we can essentially fit the model to these 2 data points. And if we drag it to just the right spot, then we're able to perfectly predict exactly where the planet is going to be and exactly when it's supposed to be there, according to these 2 data points. So that sort of, hopefully that explains where this idea of the eccentric or the off-center orbit came from. But that wasn't enough, because people like Ptolemy was fairly rigorous in his approach. He wasn't like Jason mentioned, he had a fairly substantial data set. And when he added, if you just add a few more observations, then you can see that this, should we go to, or I'll take questions in a minute. I just want to get through this demonstration. If you add 2 more observations to this data set, then we can see that we've fit the same 2 observations perfectly as before, but these other 2 observations were now, overshooting one. So we're predicting that the planet will be further along in its orbit than it's supposed to be at the time of this observation, and we're predicting it won't be far enough along at the time of this third observation. So just the idea of the off-center orbit alone won't fix this problem. Once we have this much data, then you can drag this around and you can kind of get it a bit close, but it's really not going to be perfect. So that's where this idea of the equant comes in, which Jason mentioned before. And once you add both the off-center orbit and the equant again is like this clock. I've represented it here as a clock because it really measures the angular velocity of the planet's location with respect to time. So yeah, if you look closely, you'll see that this dotted line is rotating about this clock at a constant angular velocity. And then once we have both the eccentric, the off-centered orbit, and the equant, then we can actually perfectly fit this data set of 4 points. And I'm just showing where the fitted points are because I have trouble to find them exactly. Yeah, so that allows us, it's sort of like having another degree of freedom in your model. So I think if you look at, if you take another look at the Copernican and the Ptolemaic models, you can start to understand where these concepts come from. Why would you invent something like the equant? It doesn't really make sense. You can't observe it. You can't see it. Why would you invent this mathematical construct? The most likely reason I think is essentially to fit this data set. And then of course you can keep adding data, and you'll see that if we want to be really precise about this, we want to really match these observations down to the degree or the minute or whatever you want, that even these two constructs together won't work. And then, Copernicus and different predecessors of Kepler, they keep adding more constructs. They add the epicycle. So you have just another off-centeredness. Now you have an off-center, not only the center of the orbit is off-center, but the planet itself is off-center. And that gives you a whole nother degree of freedom, and you could probably fit this model. But the point is that that I think what Kepler really gets across in part one especially is that you have a toolbox that has different tools in it. The eccentric is a tool, the equant is a tool, and the epicycle is a tool. And what his predecessors have done is basically just come up with different combinations of different tools and different, essentially different combinations to fit different models. But of course, if you it's a question of, one, how much data do you have, but also what is your actual goal here? Is it just to predict, where the planet is going to be relative to the sun at a particular time, or are you trying to do more than that? And yeah, I guess we should probably leave some of these other anecdotes for Wednesday, because I think these are really good if you read on in the anecdote that we just read, but for now I think we can leave it at that. And I see there's a question. Richard Burden, do you want to go ahead? Should we?
Maybe click and unmute.
Oh, ask to unmute. And then.
That's fine. Then just.
Yes, well, I mean, the reason why the Ptolemaic model, the Copernican model, and Tycho Brahe's model, and the vicarious hypothesis are all unsatisfactory, even if they predict observations within the range of the accuracy of measurement, is that none of these offer a reason why the planets should move the way they do. They just say, oh, they move in circles just because. Or they move around a point in the middle of nowhere just because. And this is at the center of fraud in every area of inquiry. It's where you get political pogroms. These people are barbarians just because, they're inferior to us just because we say so. Nobody gives any reason. Or if they make up a reason, then it's not subject to examination. They say, oh, they're genetically inferior. Evidence, please. You know.
Yeah, that's a good point. I think well, one thing I'll say is that if you're just observing, watching Mars go through the night sky over the course of years, it's not unreasonable to say, yeah, I think it goes in a circle, because you can't really you can't observe directly that it's an ellipse. So I think it's not totally unreasonable for them to have started with that as a baseline hypothesis. It's only when you start looking closely at it and take a data-driven approach that you can see that, okay, something isn't right here, and that's what Kepler did, and that's how he arrived at his eventual conclusion. Yeah, thank you. Do you want to
Yeah, sure.
hop back in?
Good. Thanks, Adrian.
No problem.
Yeah, I mean, you posed the, so Adrian showed the, as far as they did go, they had the epicycle, the eccentric, the equant. What if you had another epicycle and another epicycle and another epicycle and another epicycle? Is that going to be, well, I'll tell you, that's not what Kepler does. He doesn't think that's the path to truth, just making these little adjustments and adding things that are all imaginary. He says, no, we have to look at the cause of the motion. So to do that, he switches from geometry into physics. And so what we're going to do is, there's obviously much more to say about Kepler, but we're going to bring today to a close by reading some of Kepler's quotes on gravitation and on the power of the sun and how the sun actually causes the motion of the planets. For Copernicus, the sun just is sitting at the middle, but it's not doing anything. It's just there. For Kepler, the reason the planets move around the sun is because there's something physically special about the sun that's related to their motions and their speeds. So we're going to read, and I broke my rule because it was Diane. I promise if you read, I will not ask you to put it in your own words. Unless you're one of my most dear friends, and I know you wouldn't mind. So let me ask if someone can read. We're going to read the quote from 23 to 24, pages 23 to 24. It appears on page 3 of the handout. First, let me just take a look at the chat and see if there's anything that I ought to add. Why was Kepler obsessed with? The full moon has a diameter of about 30 minutes of arc. The Inquisition condemned Copernicus and Galileo because they had a different view of what the church told at that time, the dogma. Today we are on the shoulders of giants, Hawking's, who had in mind the greater good of humanity by thinking out of the box and sharing their ideas. Cusa had already expressed similar ideas. This is from Eugene. Barbara, where do I find the package of text? Good question. It is at the course website, larouche.info/science. And Richard Burden posted the direct link in the chat. Okay. I feel like my brain is breaking. This is a high intensity workout for the mind. There's a lot that we went through. Yes. There's a picture posted. Very cool. Didn't the earlier astronomers, this is Joe, didn't the earlier astronomers assume that a perfect God could only plot the course of the moving stars in circles and circles within circles because the circle is a perfect shape? Yes. In fact, we didn't get into this, but that equant that Ptolemy used to cause Mars to speed up and slow down, Copernicus hated it. He said, something changing its speed in the heavens? The mind shudders to think about it. That's like literally his language. He says, forget it. So instead, he adds actually a couple of more epicycles. So in the end, Copernicus has more epicycles than Ptolemy does. Okay, that's that question. How does Kepler figure out that the orbits are not circles but ellipses? Stay tuned for Wednesday. The data-driven approach is garbage. We need to make hypotheses about the cause, then test that hypothesis. Orbits are still kind of circles, says Morgan. Just ellipses are circles at different positions that would not appear as circles from the Earth's view. It is true that if you look at a circle kind of at at a tilted angle, that does look like an ellipse. And you could stand somewhere where that one planetary orbit, if you traced it out, in space, would look like a circle. But you couldn't do that. There's no place you can stand to make every orbit appear to be a circle.
At the same time.
At the same time, yeah. And okay, good. So let's get this reading. Bottom of page 3 in the handout. It says it's labeled 23 to 24. And let's start. If there's anyone on Zoom who would like to volunteer, you have a few seconds to raise your hand, or we'll go to the room here. 3, 2. Kevin Pearl raised his hand. Okay. Kevin, lead us off, please.
Can you hear me?
Yes.
Okay, wonderful. 23, 24. A mathematical point, whether or not it is the center of the world, can neither affect the motion of heavenly bodies nor act as an object towards which they tend. Let the physicists prove that this force is in a point which neither is a body nor is grasped otherwise than through mere relation. It is impossible that, in moving its body, the form of a stone seek out a mathematical point, in this instance the center of the world, without respect to the body in which this point is located. Let the physicists prove that natural things have a sympathy for that which is nothing. Nor again do heavenly bodies tend towards the center of the world simply because they are seeking to avoid its spherical extremities.
Oh, heavy bodies.
Oh, sorry. Nor again do heavy bodies tend towards the center of the world simply because they are seeking to avoid its spherical extremities. For compared with the width, their distance from the extremities of the world, the proportional part by which they are removed from the world's center, is imperceptible and of no effect. Also, what would be the cause of such antipathy? With how much force and wisdom would heavy bodies have to be endowed in order to be able to flee so precisely an enemy surrounding them on all sides? Or what ingenuity would the extremities of the world have to possess in order to pursue their enemy with such exactitude?
Thank you. So this, just a note on the terminology. When Kepler's saying world here, it can mean the universe, it can mean the earth. In this passage, it mostly means the universe. He's here countering, I believe, Aristotle's view of gravity, which, because people are saying, why do objects fall, right? So obviously people notice that. Isaac Newton wasn't the first person to notice that things fall, right? So obviously people came up with explanations for this. Among those explanations was everything wants to be in the center of the universe, which is in the middle of the earth. And that's why things fall. Or, and Kepler's saying, well, a mathematical point, how are bodies going to know where this point is to even try to, go towards it? And then if people say, well, no, the reason that things fall is they're trying not to seek the center of the universe, but to get away from the edges of the universe. How would you figure out how to do that most effectively? So he's not very satisfied with these explanations of gravity. So let's move on to the next quote. With a new reader, I think it's time for someone in the room here. So who wants to read the next passage? Art.
The true theory of gravity rests upon the following axioms. Every corporeal substance, to the extent that it is corporeal, has been so made as to be suited to rest in every place in which it is put by itself, outside the orb of a power of a kindred body. Gravity is a mutual corporeal disposition among kindred bodies to unite or join together. Thus, the earth attracts a stone much more than the stone seeks the earth. The magnetic faculty belongs to this order of things. Heavy bodies, most of all, if we establish the Earth in the center of the world, are not drawn toward the center of the world because it is the center of the world, but because it is the center of a kindred spherical body, namely the Earth. Consequently, wherever the Earth be established, or whithersoever it be carried by its animate faculty, heavy bodies are drawn toward it. If the Earth were not round, heavy bodies would not everywhere be drawn in straight lines toward the middle point of the Earth. Would be drawn toward different points from different sides. If two stones were set near one another in some place in the world outside the sphere of influence of a third kindred body, these stones, like two magnetic bodies, would come together in an intermediate place, each approaching the other by an interval proportion to the bulk holes of the other. If the moon and the Earth were not each held back in its own circuit by an animate force or something equally potent, the Earth would ascend toward the moon by 1/54th part of the interval, and the moon would descend toward the Earth about 53 parts of the interval, and there they would be joined together, provided, that is, that the substance of each is of one and the same density. If the Earth should cease to attract its waters to itself, all the sea water would be lifted up and would flow onto the body of the moon. The orb of the attractive power in the moon is extended all the way to the Earth and calls the waters forth beneath the torrid zone, and what it calls them forth into its path, wherever the path is directly above a place. But the moon passes the zenith swiftly, and the waters are unable to follow so swiftly. Therefore, a westward current in the ocean arises. For it follows that if the moon's power of attraction extends to the Earth's power of attraction all the more extends to the moon and far beyond. And accordingly, that nothing that consists to any extent whatever of terrestrial material carried up on high ever escapes the mightiest grasp of this power of attraction. Wow.
Wow. Okay. Why wow? Say more, Art.
I didn't know he was so explicit about this concept of gravitation.
Let me ask. Does anybody know how old Isaac Newton was when Kepler published this book?
Negative.
Negative. Does anyone know how old Isaac Newton's dad was when Kepler published this book? 3. So this is just well before, yet nobody, why have you not heard that Kepler said this, right? So,
Before the existence of apples.
well, yeah, apples, that's why, yeah, there weren't any apples. Yeah. Now, in addition to this, let me just weigh in on a few of these things that he said. He said that if the Earth weren't round, then heavy bodies wouldn't all be pulled towards the same point. Well, he's right, they aren't. If you took all over the Earth and looked at what locally down was, it doesn't point at the same location all around the Earth. The Earth's density is different and so forth. So that's certainly true. He says that the two bodies would approach each other and stick at what's their center of mass. That's true. Even the number that he gave for the Earth and the Moon, he says that if the Earth and the Moon just started, if they weren't moving and they just started attracting each other, the Earth would move 1/54th and the Moon would move the rest. The actual number would be about 1/83rd. So even there is pretty close, pretty close. And then the tides, right? This is the first real explanation, first person to really explain the tides and how the moon is causing them. People noticed the moon was associated with the tides, but now he's got like a specific idea. And I love this image of if the Earth stopped attracting the water, the moon would slurp it all up. It's fun.
Earth's gravitational pull is stronger than the moon. The moon still has a gravitational pull.
It's strong, and the water's like right next to the Earth too. So, okay, there's one more comment here, and then I want to read one more part from the book about the motion of the planets. Julian, and when the new hypothesis is tested, would you not get new data? So that over a long term, you have a back and forth between these two positions? Yes, excellent point. Whenever you're getting data, you never really just make a pure observation. It's always filtered through your hypotheses and assumptions, at least certainly in astronomy. Take, for example, when you measure the position of a planet. Planetary positions, as we saw in that passage with all of the signs and degrees and so forth, they're related to the signs of the zodiac. The planetary position is given with respect to that ecliptic circle, but it's also given with respect to where it is on the circle and then how far north or south, its latitude. Is that the best way to understand every planet's orbit? By measuring it with respect to the Earth's orbit? Because that's what we're doing. When we measure things with respect to the ecliptic, we're saying we should understand how tilted Mars is with respect to what? With respect to the Earth's orbit. So even making that measurement of longitude and latitude is making an assumption. And Kepler, at the end of this book, he says, no, we shouldn't do that. What we should be measuring the planets against is he said that the sun spins. This is before anybody had seen this happening, before sunspots, or right around the time they were first seen. Kepler said the sun spins, and its axis of spinning, that should be against, you should be against that you measure how tilted the planetary orbits are. So, so Julian, that's one example of how your hypothesis changes the kind of data that you get or the way that you look at it. David says, Kepler already had an idea that celestial bodies were sort of similar to the Earth and not just spots of light in the sky. Yes, yes. So again, before the telescope, before anyone had actually seen that the planets had some size, Kepler said that like the sun, which clearly has some size, and the Earth and the moon, Mars also was a physical body. And maybe we'll get more in on Wednesday in terms of how he explained how that relates and why it causes its distances to change and it moves in an ellipse. And then Gretchen says, Kepler is very funny. I agree. He's a really fun guy. Although not every portion of reading this book is fun. I think it's very challenging. Okay, last thing is I did not put this in the packet. I'm sorry. And it looks like there's only one book in the room here. I'm just going to read this. This is a short bit from, okay, so to come back full circle to what we heard from LaRouche in the beginning. He had said that Kepler developed an infinitesimal and that reminder to everyone, please set your phone to vibrate and leave it that way forever. Okay, so Lynn said that Kepler developed this idea of an infinitesimal that brought about the elliptical orbit, and that this is then what Leibniz built on in creating his calculus. So let's talk about what this infinitesimal looks like. How does Kepler explain the motion of the planet from moment to moment? So this is from chapter 33 of the New Astronomy. I didn't type this up. Partly it's out of respect for the translator because this book is in print and Bill Donahue did a great job printing it, and you know, you can only include but so many excerpts of copyrighted books, right? So Kepler says, which body is at the center of the universe? Is there none, as for Copernicus when he is computing, or for Tycho in part? Is it the Earth, as for Ptolemy, and for Tycho in part? Or finally, is it the sun itself, as I, and Copernicus, when he is speculating, would have it? This question I began to discuss in physical terms in part 1. It was I there supposed as one of the principles what has now been expressed and geometrically proved in chapter 32, that a planet is moved less vigorously when it recedes from the point whence the eccentricity is computed. To rephrase that last one, the planet moves slower when it is further from the sun. So fundamentally, what Kepler comes to is that the way a planet changes its speed as it goes around the sun is directly related to how close it is to the sun. Closer to the sun, you're going faster. Further from the sun, you'll be going slower. Now, in every moment when the planet's moving, doesn't its distance from the sun change? Not if it's in a perfect circle right around the sun, but otherwise, basically at every moment, wherever far the planet moved, its distance from the sun changed. So here's the question. You say, okay, the planet starts here at this distance, so I know how far it will move in 1 hour. This far. It's slower because it's further from the sun. It'll go this far in 1 hour. During that 1 hour, its distance from the sun changed. So maybe you should say, okay, let's just make it go for 1 minute, and then get the new distance and use that for the next minute, and then use that distance and let it move that far in the next minute. But during a minute, the distance of the planet from the sun changes. So maybe we should do it every second. You could keep going forever, right? And you'd never end. This is the infinitesimal. You've got what's fundamental is not a geometrical circle or a circle on a circle or a circular angular speed pushing something on a circle, on a circle, on a circle. It's none of that. It's a physical cause based on, we heard some of the physical idea of gravitation here. He's got other ideas too about sun and magnets and so forth. And the effect of that physical cause is to create an always changing speed that results in an orbit. So this is what Kepler has brought to the world, an astronomy based on causes. He abandons Plato's cave. He says, we're not going to explain the shadows. We need to know what's actually happening. He gives a hypothesis about how the sun causes the motion. And he realizes that in trying to put into practice that cause, the mathematics can't handle it. There's no language for even talking about if the change is always itself changing, what's the overall result? So I think we'll leave it. We'll just see what kind of discussion there is today. We definitely did not finish the book, and on Wednesday we can get more into some of the things we've already covered, and also we'll take a quick tour of some of the different, not shapes that Kepler tried, but the different physical hypotheses that he made for what would determine the shape of the orbit. And there were a lot of different shapes that resulted from this as he was on his way to figuring it out. Actually, I'm going to do one more thing. I'm going to read I'm going to reread a paragraph from the initial Lin paper, because I just think we covered so much of what he had said here. So I'm going to read on the top of upper right of page 2. Let's put the PDF up. Okay, we'll go with that much said. That much said, it is sufficient for the purposes of the present report to focus on a narrow but crucial feature of Kepler's discoveries, the implications of the observed Mars orbit in terms of reference to the cyclical alignment of relations among the positions of the Sun, Earth, and Mars. Now, I bet that didn't mean much when we first read it, but do you know what Lynn is referring to here about the cyclical alignment of the Sun, Earth, and Mars? Why is that important for figuring out Mars's orbit?
Because you were saying you want to get off the Earth, so you have to look at it when the Sun, Earth, and Mars are aligned, so it's from the center.
Exactly. When the Sun, Earth, and Mars are aligned, we see Mars where the Sun would see Mars. So that's what Lynn's referring to here. And then just one more paragraph. To reduce the matter to essentials, we may say, the generation of an elliptical orbit of Mars was recognized by Kepler's measurements to be the result of what Gottfried Leibniz was to make his unique discovery, his definition of the differential of the infinitesimal calculus. Simply said, the notion of the infinitesimal, which Kepler presented to future mathematicians, was a reflection of the observed consistency of the fact that the area subtended by the sweep of the orbit of Mars relative to the Sun varied in an ordering of equal areas swept during equal times. In other words, the elliptical orbit did not determine the motion of Mars. Rather, the relevant, perfectly infinitesimal principle of physical action generated the elliptical orbit of this specific characteristic, the characteristic of equal areas swept within equal times. So, okay, so that was, wow, it's after 1, and we did, okay, that was a lot. So if you want to raise anything on Zoom or in here, raise your hand on Zoom, raise your hand here. No, we can trim it off later if it's we can keep it going. It's okay. I don't know if we're monitoring the YouTube stream. If you're leaving comments on YouTube, I'm not seeing them anyway. So join Zoom next time if you want to weigh in. Oh, sorry, I'm giving preference to Zoom people here. So Joe Jennings and then Nancy. Go ahead, Joe.
Yeah, hi. Hi, I'm here with Betty, and she did ask a question. Everything that Kepler did with Mysterium Cosmographicum, the polyhedrons, determining the orbits or giving a certain, that all came long before this, what we're looking at today, correct? I mean, was that his first? Can you situate that when that happened?
Yeah, the Mysterium Cosmographicum he wrote basically when he was in college. So it was at least 10 years before this. Yeah. Did you have a follow-up? Okay. All right. Let's see here, Sarah. Okay, thank you, Sarah. Thanks for joining. See you on Wednesday. Was there something about the Mysterium you were wondering, or just when it was published? Oh, you got to ask it on mute again. All right, go for it.
Well, he didn't have any of the Tycho Brahe data available to him when he put forward that hypothesis, correct? Or what was he working from?
Yeah, that's right. So so what Joe's referring to is that Kepler, this wasn't the New Astronomy, this was not Kepler's first book. His first book, big major book, was the Mysterium Cosmographicum, the mystery of the universe. And he was asking a different astronomical question in that. He said, okay, why do we have only 6 planets? Not more, not less. That's how many you can see without a telescope. And why are they these distances from the sun instead of others? Why is Mars 1.52 times, why is its orbit 1.52 times the size of the Earth's orbit? Is there a reason for all of this? And he had put forward a hypothesis of an orbit as being like a sphere within which you would put one of the platonic solids, and then the sphere that fits inside that would be the next planet, and so on. So between Saturn and Jupiter, the outermost 2 planets for Kepler, there was a cube. So if you took a sphere with the radius of Saturn's orbit size and put a cube within that sphere, and then a sphere within the cube, that sphere would be the size of Jupiter's orbit. And the numbers look promising, but he said, of course, that astronomy wasn't that accurate, and he was using Copernicus, who used the mean sun. So already in college, Kepler was not happy about this mean sun thing. So he had his basically math teacher, mentor, help him recalculate the planetary distances based on using the real sun, but it was just a guess. I mean, you didn't really know unless you had the data for it. So yeah, in part to answer that question that he was thinking about when he was in his early 20s, here's Kepler working for the Holy Roman Empire, and he is, by the time the book came out, Tycho Brahe had died, he became the imperial mathematician. And part of his emotional impetus to figure this out was that only by actually knowing the orbits of the planets could he then come back and ask himself whether he had some insight into how God had created the universe. So he had a very big view of this. Also, he specifically mentioned here in the Mysterium Cosmographicum, already in that book, he had said the equant, he didn't like the equant. He said, I think the equant is imitating something else. I think the sun is making the planets move. And we should look at how far they are from the sun, and that'll tell us how quick they are. So he already had that when he was, I don't know, 22, 20, whatever age he was. And then now in this book, he gets to actually he has the data, he has access, and he's able to actually answer that question. So he's very excited about that. Julian, and then we'll go to Nancy. Julian asks, what is the portion of the new astronomy is the best to read? Just what you have in this packet or any additional? Well, this packet is a very small part of a very, very big book. Like literally, it's huge, which is nice, makes it easy to read. I would just start with the introduction. If you have the book, Kepler summarizes the whole thing in the introduction. I would say go through it. Sometimes with complex texts, it's good to take it like a play or maybe a movie or a big piece of music like a symphony. First time, just listen to the whole thing. Mostly just read through the introduction, think about it a little bit on the way, but don't get hung up. Just keep going. Sometimes it'll make more sense after what you get to later and see what you can pick up as a gist of it. For example, in the packet, these page numbers in the 20s, where he talked about gravitation, that's from the introduction. His statements about why you shouldn't drag the Bible into physics class, it's not a physics textbook, that's in the introduction. So I would start with that. And then this is another case, like with Plato, where at the conclusion of this class series, I'm going to send out a survey and see what kind of interests people have, and we can set up reading groups for, if there's enough people, we can set up a Kepler reading group, and get together regularly on Zoom like this. So that's what I would say on that, Julian. So let's go to Nancy.
I was just
the astronomers that the orbits had to be circled because that's the perfect godlike shape. But a circle is defined by everything being equidistant from the center.
Mm-hmm.
So how did they justify taking a circle and offsetting it if the whole point of the circle is from the center to the perimeter? It seems to me that alone should have really shaken people up in terms of what they were trying to describe, because they're saying this is God's perfect creation, but we're just going to move it over here because God wasn't totally perfect because that's not at the center.
it doesn't revolve around.
Know what I'm saying?
It shows
They didn't really believe what they were saying.
It's interesting. It's interesting.
If you like,
Or they said God's perfect and he was just, being perfect over here. From the Sanders, we have a note, only an infinitesimal number of the billions of people who have learned the calculus know the origins of the infinitesimal. I think Leibniz will forgive your misuse of the infinitesimal in the first part of that sentence, but it's humorous. Yeah, Rick.
Why does Newton get so much credit for this stuff?
Question.
Most of the century ago, your textbooks, what it's all about is find Newton-based contributions, but you have direct evidence here about gravity. But this quote, as Art said,
I'll repeat this, don't worry.
say something. Wow. Yeah, wow.
That's a quote. So the question is, why do we only hear about Newton? You read books and you read Newton, you don't hear about Kepler. Why does he get all the credit? So that part of that, there's a political answer to it that I don't really feel fully qualified to. I'm going to give a partial answer. This is definitely only a part of it. So one of the things is that Kepler was sort of poo-pooed as a mystic. This thing about the Platonic solids and all that, people said, yeah, okay, it's great that he was, when he wrote this book, he was being a scientist. When he wrote the others, he was being a weirdo, and that's not physics, that's not science, that's just strange speculation. Kepler's full theory in here is not entirely correct. He is throughout guided by physical hypotheses. He won't accept anything except for a physical hypothesis, but they're not all accurate. So, for example, Kepler's idea of inertia was incorrect. Kepler believed that bodies would naturally come to a rest. And that's not true on its own. So in other words, he didn't have it all. There were things that Newton said that were more correct than what Kepler had. To me, the question is, but why do you never hear that Kepler did any of this? And I think that is a history or political, history kind of research project to really get a good answer to that. I mean, why was Leibniz developed the calculus. Newton may have simultaneously come up with something similar, that's what they say, but how come you only hear about Newton inventing the calculus? Where's Leibniz? Again, a similar question. What was the political advantage of creating this real cult around Isaac Newton? If you look at his grave in London, it's this it's a very bizarre statue. It's definitely like a cult-like kind of a thing. Let's go with Martin. Yes, and then Martin.
The
Sorry.
people can understand better if they read Kepler or Leibniz. And if you want to get people a little stupid and a lot of stupid, you make them read other science.
What they really do to
Make maple stupid is you don't read any scientists. So, I mean, people say that, Newton did all this. Do you ever read any Newton? No. No, you don't. Here we are. We're reading Kepler. In a couple weeks, we're going to be reading Leibniz on the calculus. Where did this idea come from? The guy who figured it out wrote about it. Why don't we just read what he said and then know where this came from? Get his view of that. So, yeah, Martin first. Go ahead.
Yeah. So what I was thinking about is more philosophical idea that this discovery has been held back. Perhaps it's a speculation on my part, but this discovery has been held back by this perhaps a little bit egocentric idea that we must be in the center of everything. And by letting this idea go that we are perhaps not the center, we are able to see much, much more. And perhaps this idea being applicable to other domains as well, by saying, all right, perhaps we're not right, perhaps we're not the most important part of the problem, and then seeing much more, as opposed perhaps as well in domains of, for example, solving political problems by listening to what other people have to say, and by being open to that. That's what I got, like my impressions of the last days, also talking to people on the streets as well, to be sensitive to what people are thinking and saying, and to develop the idea based on that and not based on my own worldview. And then having this kind of bias, like everything has to fit my own picture, and then you end up most likely with wrong theories. So it's a conclusion I had.
Yeah. Well,
just to reflect on the composition of the Astronomia Nova. So, Aristotle lectures. You read his book, he's like, this is how it is, this is how it is. Plato, we read last week, everything has to be a discovery. In one of his dialogues, or purported to be one of his dialogues, the Alcibiades, he's talking to a guy who thinks he knows everything. And he said, do you remember when you discovered that? Like, was there ever a time that you didn't know everything, essentially? And the guy's like, I can't really think of anything. So he's like, well, unless it's a discovery, you don't really know it. It's one of these axioms or definitions that you're starting with, like that Lynn called out in the beginning in that passage. He said, no, it's always got to be a discovery. So when Kepler writes this book, it's not written as a dialogue, although a later book of his, The Epitome of Copernican Astronomy, actually is written like a Platonic. It's Q&A is the way he wrote it. But this one, Kepler says, when you read about history, okay, you're reading about history. You're reading about the battle. You're not there in the trenches. If you work through this book, you're with me in the trenches. We're going to do the calculations together. You're going to see exactly what I went through and be able to directly experience it. So he includes plenty of wrong ideas. Most of part 4 is he's trying to figure out how, if the planet's not a circle, then what would cause it to change its distance from the sun at all? How would that physically happen? He tries out tons of ideas. He printed the wrong ideas in the book. Because what is he trying to get across? He doesn't just want to say, here's the model. He wants to say, here's how I figured it out. He's excited to share that with you.
Yeah, just to add to that, I mean, if you read the Theaetetus dialogue, that includes this really important idea that what is knowledge? Is knowledge not obviously knowledge? Well, the first part of that dialogue is about, is knowledge just sense perception? Okay, no. Is knowledge just opinion that's true? Well, what if knowledge is actually opinion that's true with an account of how you came to that opinion? So that's sort of that's kind of the conclusion they come to, is that in order to have knowledge, you have to have truth with an account. And then, just a couple of points about Newton. Yeah, if you think Aristotle is dry, then try reading Newton. It's really bad. It's interesting. I think you should try to read like the first few pages of his Principia, just to compare it to like Leibniz. It's very interesting because he just comes out like law number 1, law number 2, and then also the idea that Kepler is a mystic. I mean, once they cracked open Newton's test, they were like, "What the hell is this going on?" So yeah, that's really, really strange stuff. And then just another point, if you want to give people because your stuff is online now again, so
Yes.
should send people a link, and then you could also send the link to mine as well.
Okay. Yes, I'll do that. I'll put on the course webpage the link to Adrian's demonstration. It's live. You can play with it yourself, and also the link to the animations that I was using. The video that I played a clip of, that's part of the playlist that was sent out and linked on the website for the class. And also the website animations, the interactive ones, those are also available at the link on the website. And I'll include all of this again in the follow-up email.
Is there a recording of the Wednesday discussion?
There is a recording of the Wednesday discussion. I didn't put it on YouTube, but I guess I might as well. So
Yeah.
I'll make it unlisted and send it to people who are registered.
Thank you.
Okay, there's 4 comments and 1 raised hand on Zoom. So let me take the written ones and then we'll come to you, Roger. Dennis writes, is the infinitesimal of Leibniz?
Dennis writes, is the infinitesimal of Leibniz discovering the true principle underlying instantaneous change, which you will discuss in the future, and which Kepler called for, is that the actual basis for the concept of physical least action, which could also be called the economy of action. So yeah, these two concepts of the infinitesimal and least action, they really do go together in terms of the kind of concept that they are. And I think I'll just sort of leave it as a teaser then to join the class the next 2 weeks for everybody, because we're going to next week get least action with Fermat, and then in 2 weeks we're going to see what Leibniz has to say about the infinitesimal or the differential. Julian says, it seems to me that Newton gets credit due to the British having the world empire during that time in history, unlike any of the European continental countries. So Newton got more airplay. That's definitely a part of it. That is definitely a part of it. My reminder to please set your phone to vibrate forever. Patricia writes, keep in mind that Alcibiades was a young aristocrat who has declared to Socrates that he was going to enter the leadership of government. So his unexamined assumptions would have a huge effect on the Athenian population. Yeah, Pat, that's a really good point. In Plato's dialogues, the people that he's speaking with, they're real people, and often they're very important people. So you see through Socrates' discussions with these individuals, the internal problems that cause the decay of Athens. So thank you for bringing that up. I'm going to read one more online thing here, and then I'm going to go to Roger, and then we got Matt. Thank you. This is difficult stuff, and okay. You're welcome. Okay, let's go to Roger. Go for it.
Can you hear me?
Yes.
Okay. I just wanted to point a couple things out. In our choral work, we've been singing a lot of requiems, and there's always a discussion of Celi et terra, heaven and earth. and that one of the key things that Kepler does is to demolish that distinction. If, people have asked this question, well, why would Ptolemy or Copernicus, when you think about having circles rotating about empty points in space, which themselves are rotating around something else, that may sound a little ludicrous, but if this is heaven, if this is God's realm, mere human beings can't know how God thinks or how he would have constructed the heavens. So you could simply sort of gloss over all these rather ludicrous explanations by saying, well, the planets are moved by angels. The planets are simply moved by God. And who are you to suggest that you could ever understand that? And Kepler very explicitly says, I want to know the thoughts of God when he created the universe. And that when he addresses this idea of physical cause, he's connecting the physical causes that we can see, we can test on Earth, falling rocks or things of that sort. You could swing a rock around your head if it's tied to a rope, but it's not going to swing around, by itself. So that he's insisting that this is something that can be investigated by the mind of man. And that itself is a revolutionary advance to say that, yes, we can understand this, and that we can put it to the test. And you may get into this later, but William Gilbert had just published the book De Magneta that discussed the idea that the Earth itself was a magnetic body. And even though people had known that compasses had existed for many centuries, that you could magnetize a needle and use it to direct your boat or whatever, that the idea that the Earth itself was a magnet that wasn't known, Kepler suggests that, well, maybe that's the reason why the planets are attracted and repelled in their path around the sun. So I think that we have to fully appreciate the revolutionary nature of that allowed Kepler to make the investigations that resulted in the so-called Kepler laws, which are somehow completely divorced from the method that he was using to actually make those discoveries.
Here. Thank you, Roger. Let's go with Matt.
Alcibiades shows up in the symposium at the very end, and he makes ridiculous claims about Socrates. But he also, his real history is that he sold out Athens to Sparta and then sold out Sparta to somebody else. He just had made a career of militarily selling out each nation that he worked for. So it was like no loyalties, just constantly screwing everybody he could to make a profit. And then when that crumbled on him, moved to the next deal.
I got to say, I think that this connects with the idea that truth is beauty and beauty is truth, because many people in a philosophy class or something, they might think, well, morality is one thing, philosophy, truth is another thing. They're not the same thing. You might want to know, a scientist wants to know what's true, some moral philosopher wants to know what you ought to do. Well, they're really not distinct. The process of coming to know something universal, when you really come to know it, when you really come to discover it, a lot of things come with that. One is a desire to share it. I think it's natural. When you figure something out, you want to share it with people. If you figured out something that's useful for society, you're having an impact on potentially the lives of everyone to come. The development of the steam engine, that has had a profound impact on everything humanity has done, right? So the you know, truthfulness, a method of discovery, I think is definitely connected to, as a personal story, after really going through this book, and making or being part of the team that made the web pages and the animations and everything, I really felt like, okay, you know what? Like, this for me is a really great moral foundation. I could just tell that I was like, okay, I feel much more empowered to do what I think is right, you know. So that's my experience. Madeline, and then we'll go to Mary Jane. Quote.
It says, right, what you know cannot be taken away from you.
What you know cannot be taken away from you.
Away from you. They can strip you of everything today, but not your knowledge. I was wondering because two things. Kepler already wrote when he was in school, apparently an essay about his thinking about the planetary system, that there's a certain amount of planets and blah, blah, blah. And then this idea of planets moving in perfect circles, because God created the circle, whatever. It was already established by Kusa earlier that planets, or that the creation is not perfect. It couldn't be perfect because it's created by the creator, imperfect. Only the creator is perfect. If that was that Kepler might have formed a certain idea about the planetary system based on this conception. And secondly, this mysticism that is put on Kepler, but also other scientists. I mean, saying he is a mystic, it's kind of, I mean, he was in astrology too. Maybe that plays a role in it, but from what I know, that there's one school form that is teaching Kepler today, and that is the Rudolf Steiner Waldorf schools that are extremely mystics. And they're teaching Kepler, and in India, they're teaching Vernadsky, which is also, I think there might be just an attempt to obscure science. When I was in school, they told us, you know, don't you remember that Van Gogh? He was a genius, but genius and insanity are so close. Didn't you know he cut off his ear? Do we really want to go there? You know,
Yeah.
maybe.
Yeah, the autistic.
Funny. Yeah, you're referring to Madeline's referring to the Mysterium Cosmographicum. That was his essay from college. Okay, I think we ought to draw this to a close. I have a couple more thoughts from, let me respond to two other things that came in already, and then Art. Okay, and then Art, and then we'll. So one was just coming back to Dennis's comment about light and least time and the infinitesimal and the connection between them. You know, the interesting thing about least time is that it's about an entire path of light. Yet it's also a principle that applies itself at every moment. At every moment, there's only one way that the light can continue moving, that is the shortest time, such that from where it began, even in this tiny moment, there's only one way it can continue. And this was a general idea of geodetics or geodesics or shortest lines that then became important with like relativity and how we move in a straight, what does it mean to move in a straight line through space-time? So that's another reflection on what we're going to be getting getting into. One more thing about Newton being a mystic. So when I was at this Kepler conference in Prague in 2009, it was for the 400th anniversary of the publication of this book in Prague. So the National Technical Museum held a symposium on it. And there was an extremely unpleasant British woman there who was just like, she would ask nasty questions after people gave presentations. She was terrifying people. She challenged me in the middle of mine, like, will you admit you are wrong about whatever, and challenged me to like a math duel, basically. which ended in a draw. Therefore, she lost because she was so nasty about it. But one of the things that she said was that Newton was the first to actually give a physical explanation, because Newton gave gravity and the inverse square law, and that's not mathematics like other people, implicitly Kepler. That's physics. And I was like, well, but isn't saying that things are attracted by the inverse square of the distance, like, why is that? Isn't that just a mathematical description of something that you observe? And I phrased it better, I promise. And she really didn't have an answer to that, because this is a problem that Newton himself addressed. You know, he writes in letters to people, well, okay, I made this claim about the inverse square law, but what is making it happen? I have no idea. The idea that things are just pulling towards each other, I mean, there's got to be something there, but I don't know what it is. So he recognized it wasn't, for him, it really wasn't a physical hypothesis. So just adding that on Newton. And then, okay, let's go to Art, and then we really are going to wrap up.
Just one little thing. You mentioned this idea that people didn't know about Kepler, but in the I looked into this guy named Ferdinand Hassler. He was the first head of the U.S. Coast Survey. He was a Swiss surveyor who worked with Gauss in Europe on surveying Europe. He did magnetic surveys. He wrote a whole book, which I've read, called A Popular Exposition of the System of the Universe in 1828. It's very similar in the scope to what Humboldt wrote in Cosmos, and even to a certain degree what Poe wrote in Eureka. He's describing what the state of knowledge was at the time. He makes a very clear reference to Kepler and how Kepler's discoveries were really much more fundamental than Newton. So he's writing this in 1828. You know, this is the period of John Quincy Adams, right? So he was the first head of the U.S. Coast Survey, and that was one of the real foundational scientific organizations in the country, right? But anyway, he wrote this in 1828. It was basically, he was describing the latest discoveries of like Neptune, you know, things like that. But, you know, he's saying, basically described Kepler and his discoveries as really taking precedence over what Newton did.
No, could you say his name again?
Ferdinand Hassler. I'll send you
Hassler, Hassler.
Yeah,
Ferdinand Hassler. Okay.
I'll send you my articles.
That's actually an interesting point.
Okay, so thanks to everyone. Final wrap-up statements here. We got a actually, that's enough. I'll just say what's going to happen on Wednesday. So what we didn't take up here was, we can read some more quotes about how he said that the sun causes the motions of the planets. We have some more on that. And we'll be able to look at how he tried to make the planets change their distance from the sun, and his different ideas on that, and whatever else we'd like to discuss at that point. So thank you all. Thank you for everyone who participated. It's this is a lot of fun, isn't it? Isn't this fun? So thanks for joining. See you hopefully Wednesday or maybe Sunday.